In our previous video, we discussed how various unit observables arise from the unit action h. When dealing with a system that executes multiple actions simultaneously, we can calculate its macroscopic behavior by adding up all unit observables produced by the system. This approach is known as the sum of all actions. While the unit action h and unit time tau are scalar, the unit length lambda is a vector with a specific direction. If an observable is derived solely from scalar quantities, it will remain scalar, and its summation follows the rule of scalar addition. A system's energy consumption is scalar. It always increases monotonically as the system evolves, which defines the arrow of time for the system. If an observable is derived from combining some scalars with a vector, it will be a vector. And its summation follows the rule of vector addition. A physical system usually executes an enormous number of actions in parallel. Combining such vectors creates complex spatial and temporal patterns, resulting in a collective system behavior that differs significantly from the simple addition of individual behaviors. This is how new and complex system behaviors emerge from the repetition of simple actions at a lower level. Let's take a look at the definition of mass. The unit mass m is defined as the product of the unit action h and the unit time tau divided by the mean squared displacement. Lambda squared, the product of two vectors, is scalar. As a result, the mass m is a scalar. Just like the energy E. The energy E is equal to action h over tau. Thus the mass can alternatively be expressed as E divided by c squared, where c is the thermal speed of a particle. Given a stable thermal environment, c remains constant. Einstein interpreted the equation to mean that mass and energy are equivalent, differing only by a constant factor, c squared. Einstein's interpretation more or less reflects the bias of a human observer. We tend to think that inanimate objects have a well-defined mass and that their motion must follow the laws of physics. But not so much for living things like ourselves. For example, while we're very aware of our weight gains and losses, we often think of rocks as something with a fixed mass. We have the will to move around freely, but rocks at rest remain at rest unless some external force acts on them. Physicists can weigh the mass of celestial objects and predict their motion accurately. But they have no idea of how their equations govern the motion and evolution of living organisms. Physicists develop theories to explain everything from elementary particles to the birth of the universe. But their theories say nothing about what goes on inside their brain, as if they weren't part of the universe. Why is that? Because we're still thinking about everything in human terms, and we unconsciously take an anthropocentric view of the universe. To overcome this bias, let's imagine that we were an observer the size of a star with a lifespan of billions of years. If we were studying a rock, we would see many of its life cycles. Its mass would fluctuate over its lifetime, just like a living organism. If we were to study a human or an animal, it would look like an atom. We would discover that its mass must stay at some discrete energy level, jumping after each meal or bowel movement. Similarly, imagine that we were an observer the size of an atom with a lifespan of a few milliseconds. If we were to study a human being or a human society, they would look like a star or a galaxy that lasts billions of years. We'd observe that they're constantly absorbing or releasing a large amount of mass. Although the absolute amount were huge relative to a tiny observer like us, the percentage change relative to the object under study would be minimal over many of our ephemeral lifetimes. We could simply treat them as having a fixed mass. All physical systems look like a living system when we study them with the proper clock and ruler. Whether or not we can see the life cycles of a subject under study depends on the units of space and time which we use to measure such systems. There is nothing truly special about the living system around us. In Einstein's mass and energy equation, the structure of space and time is encoded in the constant speed c. To treat all physical systems equally, we need to put the proper clock and ruler back into the equation. Let's move the unit of time to the left side. This equation expresses the particle and action equivalence. On the left is the unit mass m, which represents a particle. A particle of a higher level is born from particle interactions of a lower level. A particle grows by absorbing parts in the environment, and dies by releasing its parts into the environment. The mass of a particle is constantly changing. It never remains at a fixed value. m over tau represents the evolution of a particle's mass over its lifetime. On the right is the unit action h, which creates the particle on the left. The execution of an action must unfold in space. The size of the arena is measured by lambda squared, the mean squared displacement traversed by a particle during its lifetime. H over lambda squared represents the unfolding of the same particle on the left. No matter how complex a physical system is, it's made up of individual parts. The space, time, mass, and action experienced by individual parts must observe the relationship expressed in this equation. Therefore, we should be able to use it to deduce the laws of motion. Before explaining how, let's look at how the laws of motion have typically been taught for the past 400 years. While you're listening to what Feynman says, please also pay attention to what he does.
Galileo, in studying the laws of motion and doing a number of experiments to see how balls roll down inclined planes and pendulums swung and so on, discovered an idealization, a great principle called the principle of inertia, which is this: that if a thing has nothing acting on it, if an object has nothing acting on it and is going along at a certain velocity in a straight line, it will go at the same velocity at exactly the same straight line forever.
In the video, nothing obvious is acting on Feynman. Why does he keep walking back and forth and making random hand gestures? If we were to look at the muscles on Feynman's vocal cords, they're vibrating in an intricate pattern that produces his speech. Nothing about Feynman moves at a constant speed in a straight line, as the principle of inertia dictates. In light of his actions, his words don't seem to make sense anymore. We need a new physics to model exactly what Feynman is doing, and to explain the law that governs his motion. Some might argue that Feynman is a living, conscious being, and that his movement is outside the realm of physics. Let's put consciousness aside for the moment, and consider a similar but simpler system: a wildfire burning through a grassland. A wildfire moves much like Feynman. Its movement is quite arbitrary and unpredictable. It doesn't seem to care about Newton's laws of motion. If a wildfire could talk, and asked to explain why it moves in a certain way, it might say that it likes to chase fresh air, or that it wants to find more fuel to burn. This response would make perfect sense to a conscious being. If something moves like a living thing, and behaves like a living thing, we might as well treat it as a living thing. A wildfire doesn't have a fixed shape or size, and it cannot be treated as a point particle. We don't know how to measure the mass of a wildfire, let alone all the forces acting on it. To deduce the law governing the motion of a wildfire, we have to start with something really basic. As always, a physical system consists of three basic components: a thermal environment, an energy source, and a pair of action and counteraction. The thermal environment is the atmosphere. It's made up of an enormous number of jiggling molecules, including active participants such as oxygen, carbon dioxide, and water molecules, and many other inactive particles. Inactive particles don't directly participate in the burning, but they're critical to the operation of a wildfire. The energy source is the photon gradient coming from the sun. It's a form of potential energy, similar to the proton gradient that drives the synthesis of ATPs, or the electrochemical gradient that powers your brain activity. The most prominent observables in the system is a pair of action and counteraction. One action is the photosynthesis, denoted by H- here. The photosynthesis absorbs the energy from photons, and transforms carbon dioxide and water molecules into carbohydrates, releasing oxygen molecules. The energy carried by photons is trapped inside carbohydrates. The counteraction, denoted by H+, burns the carbohydrates, and produces carbon dioxide and water molecules. The energy trapped inside carbohydrates is released in the form of heat. Let H+ be the unit action that produces one molecule of carbon dioxide. Note that the unit action corresponds to a combustion complex. And it is not the same as one carbon dioxide, which is the byproduct of the action. Let tau be the average lifetime of a combustion complex, and lambda be the average size of the space explored by the complex during its lifetime. The evolution of a wildfire could be understood by summing up the motion of all microscopic combustion actions. In classical mechanics, each combustion complex is treated as a point particle, and its motion is described by its position, x, as a function of time, t, According to Pierre-Simon Laplace, if an individual knows the position, momentum, and forces acting upon all particles in a system, they can accurately calculate and predict the future of the system. However, there are some serious problems with this approach. Firstly, it assumes that space and time are independent variables, which is a very flawed assumption. Secondly, classical mechanics is incapable of handling the evolution of more than 3 bodies, let alone a wildfire that executes numerous combustion actions in a chaotic thermal environment. The problem requires a completely different approach. We'll model the evolution of a wildfire as the density of combustion actions, ρ, as a function of position, x, and time, t. The density function can not only describe the shape, size, and intensity of a fire in space but also model how the fire evolves over time. To understand the rule governing the evolution of the density function, we'll examine a small region of space with size lambda and time window tau centered at position x and time t. Let's add up all the combustion actions executed in the region. The same actions executed in the same environment share the same physical characteristics. All the combustion complexes in a small region should have the same mass m, lifespan tau, and mean squared displacement, lambda squared. On the left side of the equation, each m represents one combustion complex, and tau represents its lifespan. Since the divisor tau is the same for all, we can sum up all the dividends directly. Let curly d rho be the number of actions in the region. The total mass is equal to curly d rho times the unit mass m. Let's replace the unit time tau with a different symbol, curly dt. Similarly, on the right-hand side, the sum of h over lambda squared can be expressed as curly d rho times the unit action h divided by curly dx squared. By combining the unit mass m on the left and the unit action h on the right into a single constant d, this equation has a similar form to Einstein's diffusion equation. However, it is not yet a partial differential equation. Currently, curly d rho is defined as the number of observed combustion actions in a small region with size lambda and time window tau. It is impossible to count combustion actions in a fire via experiments. What can be measured are the byproducts of combustion action, such as changes in carbon dioxide levels, oxygen depletion, or the amount of heat or light generated. If the maximum temporal resolution and spatial resolution of an observation are the unit time tau and unit length lambda, respectively, then observing a single combustion event in a given area is equivalent to observing the production of one carbon dioxide molecule, the removal of one oxygen molecule, or the emission of one unit of heat and light in that same area. All of these measurements are directly proportional to the number of combustion actions. If we redefine ρ as the density of carbon dioxide, oxygen, heat, or light in the environment, we can reinterpret curly d rho as the change in that density. This turns the equation into a true partial differential equation. Thus, we did derive Einstein's diffusion equation through a different route. There are a few subtleties to consider with this interpretation. In our derivation, we make the assumption that we can precisely count all of the particles within a specific region. However, in a real-world system, particles are constantly moving in and out of the region. The problem is not a real issue in practice. When we conduct experiments and measure physical quantities, we never freeze the system and count every microscopic event. Instead, all measurements are based on some kind of sampling. If the sample size is sufficiently large, random movements cancel each other out, and the sample mean converges to the population mean. Rho is often interpreted as the probability density of observing a particular particle or event. The probability interpretation is more accurate and better reflects what is being measured in experiments. In our reasoning, we equate the observation of one combustion action with the production of one carbon dioxide molecule or the reduction of one oxygen molecule. However, if an observer has a resolution finer than tau or lambda, they may observe the same combustion action multiple times at different locations, which would invalidate our reasoning. Therefore, while in calculus the derivative is defined as the slope of a tangent line when dt and dx approach zero, in our probability interpretation, dt must not approach beyond the unit time tau, and dx must not approach beyond the unit length lambda. This is the same measurement limit expressed in the uncertainty principle. The density function serves as a universal tool that links microscopic events to macroscopic observables. For instance, to model the growth on a grassland, we can use the density function of the unit action of photosynthesis. By using a pair of density functions, one for creation and the other for destruction, we can model the seasonal change or life cycle on a grassland. The density function can model various phenomena, including the motion observed in this video. The movements of the subject, such as pacing, hand gestures, and speech, are all results of the contraction of muscle fibers inside his body. At microscopic level, all muscle movements boil down to a single action. When an ATP molecule binds to a myosin head, it is hydrolyzed into an ADP and an inorganic phosphate, causing the myosin head to extend and attach to the binding site of an actin filament. This triggers an action called power stroke. The action causes myosin to pull the actin filament in one direction. ADP and phosphate are released after a power stroke. When another ATP molecule binds to the myosin is detached from the actin filament, starting a new cycle of power stroke. The detailed muscle contraction in a living organism can be described by the density of power strokes as a function of position x and time t. The motion of a living organism is controlled by what happens inside their brain. The brain of a living organism contains a network of interconnected neurons. The firing of action potentials moves on the cell membrane of the network, much like a wildfire sweeping across a grassland. Neural firing is a result of two opposing actions: the flow of ions down their electrochemical gradient, and the pumping of ions against that gradient. The density function of these two actions can describe all observable brain activities. In our first video titled, Quantum Mechanics Reimagined, we explored how to use complex function phi to represent the state and evolution of a quantum system. Our second video introduced the spacetime invariant. In a quantum system, the time interval t measured in its natural units of time tau is always equal to the distance x measured in its natural units of length lambda. This relationship shall hold true for all quantum systems. Combining the spacetime invariant and Euler's identity creates the universal identity. This equation assigns physical significance to an otherwise purely mathematical expression. Using the universal identity, we can derive the wave function phi, which describes the evolution of a quantum system in terms of position x and time t from its initial state phi naught. We demonstrated that this function satisfies the Schrödinger equation. Combine all constants into constant d. The Schrödinger equation has a form that's similar to Einstein's diffusion equation. This is not a coincidence. Both partial differential equations describe the same physical system that executes the unit action expressed by the identity in the middle. The density function ρ returns a real number, representing a physical quantity that can be measured through experiments. The wave function phi returns a complex number, tracking the execution state of a unit action. A physical system typically executes a vast amount of microscopic actions that keep bouncing around and interfere with each other. The complex representation provides crucial information for calculating interference patterns. At the core of quantum mechanics lies the following question: how is the wave function phi related to the probability density function ρ? In 1926, German physicist Max Born formulated a rule, which was subsequently named after him. The Born rule states that the probability density of finding a system in a given state, denoted by ρ, is proportional to the square of the amplitude of the system's wavefunction at that state. Although the Born rule is the most accurately tested law in the history of science, its underlying mechanism remains unknown, even to Born himself. Richard Feynman, when teaching quantum mechanics at Caltech, advised his students not to inquire the machinery behind the rule, stating that it is likely to remain a puzzle forever and that it represents the way nature really is. We don't want to become what Feynman referred to as Mayan bean counters, individuals who only focus on calculation without seeking to understand the underlying reasoning and mechanisms. Rather, we strive to comprehend the how and why behind these scientific principles. In order to comprehend the Born rule, we must first review how wave function represents a quantum system. The wave function phi is a complex representation. We can visualize the complex representation using a rotating arrow. An arrow rotating counterclockwise tracks the state of ion crossing that results in an upward microcurrent. The center of the circle represents the origin of complex plane, and the horizontal line represents the real axis. The rotating arrow corresponds to complex number e to the power of plus I theta, where theta is the angle between the arrow and the real axis. Similarly, an arrow rotating clockwise, or complex number e to the power of minus I theta, tracks the state of ion crossing that results in a downward microcurrent. In both cases, the angle theta, measured in the units of 2 pi radians, is equivalent to the time t, measured in the units of the average crossing time tau. This relationship holds true for all angle theta and time t. Rearrange the equation. This formula converts the time t to the angle theta. The angle theta is equal to 2 pi times t over tau. Substitute the angle theta with 2 pi times t over tau. The state of ion crossing is now expressed as a function of time t. Phi of t equals e to the power of plus or minus I 2 pi times t over tau p, where tau p is the average ion crossing time through membrane protein p. In quantum mechanics, phi of t is known as the time-dependent wave function, which models the evolution of a quantum system over time. The inverse of a time period defines a frequency, which is equal to the number of occurrences of a repeating event per unit of time. Let Fp be the inverse of tau p. Fp defines the natural frequency of an ion channel or ion pump. The natural frequency is one of the most important properties associated with a physical object. Assume, without loss of generality, that the ion channel on the left has an average crossing time of 1 tau, and its natural frequency is 1 f. And that the ion pump on the right has an average crossing time of half tau, and its natural frequency is 2 f. Let's see how complex function phi of t tracks two ion crossings simultaneously. Suppose that, at time t equals 0 tau, an ion starts to move up the channel on the left. At the same time, another ion starts to move down the channel on the right. Because the function on the right has 2f in its exponent, the arrow on the right rotates twice as fast as the arrow on the left. At time t equals half tau, the arrow on the left rotates a half circle, corresponding to the ion crossing on the left as half done. During the same period of time, the arrow on the right rotates a full circle, corresponding to one complete ion crossing on the right. As time passes, the combined system continue evolving. At time t equals 1 tau, the arrow on the left completes a full circle, corresponding to one complete ion crossing on the left. At the same time, the arrow on the right complete 2 full circles, corresponding to 2 complete ion crossings on the right. In both cases, the area swept by an arrow is always proportional to the amount of ion crossings through the corresponding channel. If we define the area of a unit circle as 1, red area as positive, and green area as negative, we can compute the amount of net crossings in a combined system by adding up all areas swept by individual arrows. For example, per unit time tau, the system on the left draws 1 positive red circle. The system on the right draws 2 negative green circles. 1 positive red circle plus 2 negative green circles equals 1 negative green circle. 1 negative green circle means 1 unit of downward microcurrent. Thus, the temporal density of ion crossings in the combined system is 1 downward action per unit time tau. Currently, we assume that both ions carry the same amount of charges. In a living cell, some ions carry more charges than others. For example, 1 calcium ion carries 2 elementary charges, twice as much as the charge carried by 1 sodium or 1 potassium ion. Let's see how a complex function models the ion crossing with different charges. Suppose that on the right is a sodium channel. The sodium channel allows 1 elementary charge to cross at a time. Assume that its average crossing time tau r is half tau. The natural frequency of the sodium channel is 2f because 2 elementary charges flow through it per unit time tau. As we just discussed, such a sodium channel can be modeled using a complex function. e to the power of minus I2 pi times t in the units of tau, and times frequency 2f. Suppose that on the left is a calcium channel, and that its average ion crossing time is 1 tau. The calcium channel allows 1 calcium ion to cross per unit time tau. Each calcium ion carries 2 elementary charges. Thus, the frequency of ion crossing through the channel is 2f, meaning 2 charges per unit time tau. The calcium channel on the left can be represented by the complex function e raised to the power of plus I2 pi multiplied by t times 2f, where the plus sign in the exponent signifies the direction of ion crossing. Suppose an observer uses an ampere meter to study the combined system. The maximum temporal resolution of the ampere meter is coarser than 1 tau, and the maximum spatial resolution is coarser than 1 lambda pz, which is the height of protein P. For such an observer, the action observed on the left is indistinguishable from the action on the right except their directions. This corresponds to 2 arrows rotating at the same rate but in the opposite directions. To determine the net crossings in the combined system, all we need to do is count the circles and sum them up. The subsystem on the left generates 2 positive circles per unit time tau, while the subsystem on the right produces 2 negative circles in the same timeframe. Their sum is always equal to 0. This means that 2 subsystems counterbalance each other, resulting in no observable net current in the combined system. We can use the same approach to model more complicated ion crossings. For example, suppose that this is a sodium and potassium pump. For each time period of tau, it pumps 3 sodium ions from cytoplasm to extracellular region, and then pumps 2 potassium ions from extracellular region into a cell. Let F denote the base frequency of such a sodium and potassium pump. F equals 1 over tau. The complicated ion crossings through the pump can be modeled as the superposition of 2 simple crossings in the opposite directions. On the left is a channel for sodium ion crossings. 3 positive charges are pumped up per unit time tau through the channel. The frequency of upward sodium ion crossings is 3f. The ion crossing through the channel is represented by complex function e to the power of plus I2 pi times t and times 3f. On the right is a channel for potassium ion crossings. 2 positive charges are pumped down per unit time tau through the channel. The frequency of downward potassium ion crossings is 2f. The ion crossing through the channel is represented by complex function e to the power of minus I2 pi times t and times 2f. Suppose that at time t equals 0 tau, the ion pump cycle starts. We can model the ion crossings by rotating the corresponding arrows. For each time period tau, the red arrow rotates 3 circles, and the green arrow rotates 2 circles. This models 2 opposite ion crossings in one pumping cycle. 3 positive red circles plus 2 negative green circles equals 1 positive red circle. 1 positive red circle means the system generates 1 unit of upward microcurrent for each pumping cycle. If an observer measures the cross-membrane current through the pump, and the temporal resolution of his ampere meter is coarser than 1 tau, any prediction based on this mathematical model will match his observation nicely. Let phi n of t denote the complex function e raised to the power of n times I2 pi ft, where n is an integer, and f is the base unit of frequency, equivalent to 1 event per unit time tau. In quantum mechanics, the function phi n of t is used to model the repeated execution of some unit actions. N is a signed frequency, and the 2 opposite signs represents 2 opposing unit actions. For example, the channel on the left produces 3 units of upward microcurrent per unit of time. It is modeled by the function phi with a frequency of positive 3. The channel on the right produces 2 units of downward microcurrent per unit of time. It is modeled by the function phi with a frequency of negative 2. The function phi n of t serves as a basic building block to model large and complex systems. Consider a composite system comprising 5 distinct channels. 2 of these channels have a frequency of positive 3, while the remaining 3 have a frequency of negative 2. We'd like to construct a single function that models all ion crossings in the composite system. Here is how it works. We'll define the function psi n of t as the function phi n of t multiplied by a coefficient Cn. The coefficient Cn is a complex number, representing the configuration of the subsystems with the frequency of n. The magnitude of Cn is equal to the square root of W, where W is the weight or number of channels whose frequency is n. For example, there are 3 channels with a frequency of -2 on the subsystem on the right. The function representing the subsystem, psi of -2, has a magnitude that equals the square root of 3. The angle theta of the coefficient Cn represents the initial state of a system at time t0. A complete action is equivalent to 2 pi radians. Thus, the angle theta can be measured in the units of 2 pi radians. For example, suppose that at time t0, an ion just starts to cross the first channel. The initial state of ion crossing through this channel is represented by an angle of -0 pi, where the negative sign matches the direction of the action. If the ion crossing through the second channel is 75% done, then its phase angle theta is equal to -1/2 pi, or +½ pi if only primary angle between -1 pi and +1 pi are used. If the ion crossing through the third channel is half done, then its phase angle theta is equal to -1 pi. The phase angle for a combined system is the mean of the angles of all its subsystems. The angle theta for the 3 channels on the right is equal to -1/6 pi. Therefore, the coefficient for the subsystem with a frequency of -2 is the square root of 3 times e to the power I theta 2, which maps to this point on the complex plane. The complex number represents the configuration and initial state of the subsystem consisting of 3 channels on the right. Similarly, we can construct another function psi of +3 for the 2 channels on the left, and map its configuration and initial state to a point on the complex plane. As time passes, the 2 functions model the execution of actions in the 2 subsystems. For each period of tau, the arrow on the left rotates 3 full circles, and covers the area of 6 positive unit circles, corresponding to 6 positive actions executed by the subsystem on the left. In the same period of time, the arrow on the right rotates 2 full circles and covers the area of 6 negative unit circles, corresponding to 6 negative actions executed by the subsystem on the right. The total area covered by the combined system is equal to 0, meaning that the system does not cause any change in the membrane potential. To model a composite system with multiple frequencies, we can add up the complex representation of individual subsystems. This can be expressed mathematically as an equation. The evolution of a composite system, denoted by psi of t, is equal to the summation of psi n, where psi n represents the evolution of a subsystem with a frequency of n. N can be any possible frequency. If a specific frequency n is not present, psi n is set to 0. In this particular example, the system is composed of 2 subsystems, one with a frequency of +3 and another with a frequency of -2. We can represent the composition of the system graphically. The positive subsystem is represented by a red arrow, while the negative subsystem is shown as a green arrow. The yellow line equals the sum of the 2 arrows. The yellow dot represents the state of the combined system. As time progresses, the dot traces a flower-like pattern with 5 spokes. No matter how complicated a quantum system is, it can be represented by the linear combination of all its subsystems. The evolution of the composite system is modeled by the function psi, which is specified by a set of complex coefficients. If a system comprises many subsystems, the resulting function becomes exceedingly intricate. It's no longer straightforward to tally the number of circles drawn by individual arrows. A more efficient method is needed to compute the number of net crossings directly. Let psi of t be the complex representation of a quantum system. Let tau be the natural unit of time for the system, and f be the base frequency. We can define a function ρ of t as 1 over I2 pi times the derivative of psi multiplied by the conjugate of psi. This function represents the temporal density of actions produced by the system. To compute the number of actions produced by the system at a specific time t with an observational window of delta, we just need to integrate ρ over the interval from t to t plus delta. This provides a measure of the system's activity which can be tested via experiments. There is a lot to be digested here. To begin, let's consider a straightforward system that comprises only channels operating at a specific frequency. As previously discussed, such a system can be modeled by the function psi(n), which can be visualized by a rotating arrow. In this representation, the area swept out by the arrow is directly proportional to the actions generated by the system. Let dA be the area swept out by an arrow in a time interval dt. The area dA can be expressed as 1/2 of the radius r times the arc length ds. The area of a unit circle is pi, so dividing dA by pi yields a dimensionless number that represents the number of actions or unit circles. The radius r is equal to the absolute value of psi. The line connecting the two arrowheads, denoted as d psi, approximates the arc length ds. d psi approaches ds as the time interval dt approaches 0. The limit can be expressed as this equation. The right-hand limit defines the derivative of psi with respect to time t, denoted as a dot over psi here. The left-hand limit defines the temporal density of actions, which is a function of time t, denoted as rho of t. This is a differential equation that connects the density function rho with the wave function psi. Psi has the same absolute value as the conjugate of psi. We can replace the absolute value with the conjugate of psi. This doesn't change the absolute value of the product of these two complex numbers, but rotates the result by the conjugate angle of psi, resulting in an imaginary number perpendicular to the real axis. If we divide the result by the imaginary unit I, this converts the imaginary number into its absolute value, which can then be interpreted as the temporal density of actions produced by the system. Alternatively, the area dA, measured in the unit circle, can be expressed as the square of the radius, denoted as the absolute value of psi, multiplied by the angle d theta. The angle d theta is equal to the time interval dt multiplied by the conversion factor 2 pi over tau. The two pi's cancel each other out. Move dt to the left side of the equation. dA over dt defines the density function ρ. The equation states that the density ρ is proportional to the square of the absolute value of the complex representation psi. Rho represents the density of actions, which is proportional to the probability density of observing such actions. Thus, the equation expresses the rule as formulated by Max Born. When studying the scattering problem, Born discovered the relationship. However, the significance of the coefficient was not fully understood at the time. By normalizing the area under ρ to 1, Born could interpret ρ as probability density, and the coefficient became a generic normalization factor. These two equations are equivalent. In our discussion, we'll use the first one for two reasons. First, it preserves the signs, allowing us to see the evolution of two opposing actions simultaneously. This is important if we want to understand the interplay of two opposing actions in the same environment. Second, the absolute value of ρ now carries physical significance, as it represents the density of the unit action h. Its interpretation is no longer limited to probability density. By multiplying ρ with various unit conversion factors, we can compute how these observables evolve over time. While these unit conversions play a similar role to quantum operators in the traditional formulation of quantum mechanics, the math involved is simpler, and more importantly, the physics is intuitive and straightforward. No more quantum mumbo-jumbos or philosophical strugglings. Born, in his Nobel lecture, noted that Planck, Einstein, de Broglie, and Schrödinger have unceasingly stressed the unsatisfactory feature of his interpretation, and called for a return to the concepts of classical physics while proposing ways in which this could be done without contradicting experimental facts. As we've demonstrated thus far, the seemingly opposing views from both camps can be reconciled under the principle of super-general relativity. The concepts discussed here can be easily explained to high school students with a fresh mind, or to some founders of the quantum theory who remain skeptical about the statistical interpretation of quantum mechanics and the probabilistic nature of the universe. Before moving on to the next topic, we need to figure out how to apply these rules to compute the actions produced by a composite system. To illustrate the problem, consider the example where the red arrow represents two red channels on the left, The green arrow represents 3 green channels on the right, and their sum, the yellow line, represents the composite system. The subsystem on the left produces actions proportional to the square of the red arrow, while the subsystem on the right produces actions proportional to the square of the green arrow. The actions produced by the composite system should be equal to the sum of the two subsystems. However, if the Born rule holds true for the composite system, then the square of the red arrow plus the square of the green arrow should be equal to the square of the yellow line, which is not always the case unless the 3 lines form a right triangle. So, how can the same rule be applied to a composite system to compute the total amount of actions produced by the system? Here is where some calculus tricks come in handy. If we have a density function for some quantity, we can integrate the area under the curve to compute the sum. Let's find out what we get if we integrate the density function ρ for a time interval delta at a specific time t. We will use the first formula. Ρ equals 1 over I2 pi times the product of the derivative of pi's and the conjugate of psi. Let's expand the integral. Psi can be expressed as the sum of its subsystems, where n is a signed integer representing the frequency of a subsystem. Wn is the number of channels operating at the frequency n. Theta n is an angle representing the relative frame shift of action execution in the subsystem. And the exponential function, e raised to the power of n times I2 pi f times t, models the execution of unit actions by one channel in the subsystem. The derivative of an exponential function with the natural base e is equal to the function itself. We can apply the chain rule to the exponent. This moves down the coefficient, n times I2 pi f. The two terms with I2 pi cancel each other out. The base frequency f is the same for all frequencies. We can move it out of the summation. Next, let's expand the conjugate of psi. The angle theta n, or the frequency n in the exponents, could be either positive or negative. We put a plus sign before them just to emphasize that they represent the original values from psi. The conjugate of psi would flip the sign for both exponents. The product of these two summations results in n by n terms. We will divide them into two groups. One consists of n terms, resulting from the multiplication of the components from the same frequency. The other has n times n minus 1 cross terms, resulting from the multiplication of different frequencies. Let's first work out the multiplication of the components from the same frequency n. The product of two square roots is equal to Wn. The product of two conjugates, e to the power of I theta and e to the power of minus I theta, is equal to e to the power of 0. Anything raised to the power of 0 equals 1. Anything multiplied by 1 is itself. So the two conjugates with opposite angles cancel each other out, as does the product of the two conjugate functions. The multiplication of the components from the same frequency results in constant terms, which equal the frequency n multiplied by the number of channels Wn. To make it easy to work out the cross terms, we will substitute n in the first summation with p, and n in the second summation with q. The cross multiplication results in two summations. Note that the inner summation is annotated with p not equal to q, indicating this contains only the cross terms of two different frequencies. First, move the frequency p to the product. Multiply the square root of two weights. Add up the exponent of two phase angles. Multiplying the two exponential functions results in a new function, whose frequency equals the difference of two contributing frequencies. In a quantum system, all physical quantities shall be measured in their natural units. So both t and delta must be in the units of tau. Let's assume that delta equals k tau, where k is a positive integer counting the number of the unit time tau in the time interval delta. Now, we can evaluate the integral over the interval t and t plus delta. The first part contains only constant terms. To evaluate the integral of these terms, multiply them by t plus delta minus t, which equals the time interval delta. The interval delta is equal to k tau, and the base frequency f is equal to 1 over tau. The two terms with the unit tau cancel each other out. The first part of the integral is to sum up the product of three integers. The frequency n, representing the number of actions produced by one channel per unit of time tau. The weight Wn, representing the number of channels that operate at the frequency n, and the duration k, which is the time interval measured in the units of tau. This summation represents the basic counting rule. The actions produced by a composite system is the sum of all actions produced by its subsystems. The second part of the integral is comprised of the summation of many exponential functions. The antiderivative of an exponential function is itself multiplied by a constant. Note that we simplify the antiderivative by folding all the constants into a single constant, denoted as a pq. We can evaluate the resulting expression in the interval between t plus delta and t. Again, the frequency f multiplied by the interval delta results in the integer k, the time interval measured in the unit tau. The three numbers in the exponent, p, q, and k, are integers. P minus q results in an integer. The difference between p and q multiplied by integer k is still an integer. E raised to the power of I2 pi times any integer equals 1. 1 minus 1 is equal to 0. This removes the summation of all cross terms. The final result contains only the term that adds up the actions generated by individual subsystem. Therefore, if the temporal resolution of the measurement is no finer than tau, which means that all time intervals can be expressed as integer multiples of tau, this integral calculates the total number of actions generated by a composite system accurately. If we know the complex representation of a quantum system, we can compute any observable derived from the actions produced by the system. For instance, the sodium-potassium pump is a composite system that moves 3 sodium ions up and 2 potassium ions down during each pumping cycle. The system can be modeled as a superposition of two channels: a sodium channel with a positive frequency of 3, represented by phi of positive 3, and a potassium channel with a negative frequency of 2, represented phi of negative 2. We can express the composition of the system mathematically using the equation psi equals phi of positive 3 plus phi of negative 2, where psi represents the sodium-potassium pump. During each cycle, the pump generates one net positive action that results in an upward microcurrent equivalent to 1 elementary charge per unit of time. This calculation can be performed using the density integral and unit conversion. The electric current I, as a function of time t, is equal to E over tau multiplied by the net ion crossings generated by the pump over the interval between t and t plus tau. Where I of t is the current generated by the pump, E represents 1 elementary charge, tau is the duration of one pumping cycle, E over tau converts 1 unit action to 1 unit current, and the integral adds up the actions using the density function derived from psi. We can apply the same approach to model neural activity in the brain. Let H0 denote the least energetic action in a brain. H0 is defined as the action of an elementary charge crossing the cell membrane. The energy exchange is so slow that it takes the lifespan of the brain for the action to complete. This definition can be expressed in the equation H0 is equal to E0 divided by T0, where E0 is the energy exchange caused by one elementary charge crossing the cell membrane, and T0 is the lifespan of a brain. A brain defines the universe in which all neural activities take place. Just like the Planck constant is the natural unit of actions in our visible universe. H0 is the natural unit of neural actions in that universe. 1 over T0 defines the base frequency for the universe of neural actions. The base frequency F0 is the lowest possible frequency, representing rare events that happen only once per lifetime. The frequency of one elementary charge crossing a specific channel can be expressed as an integer multiple of the base frequency F0. Each distinct ion crossing is associated with a unique integer n, where n is a signed integer, with the sign indicating the direction of the action. An ion may carry more than one elementary charge. The energy exchange associated with n elementary charges crossing the membrane is n times of 1 elementary charges crossing the same membrane during the same period of time. It can be expressed as the energy En equals n times E0, where n is also a signed integer, with the sign indicating the direction of the action. For an observer with limited spatial and temporal resolution, the action of n elementary charges crossing the membrane once per lifetime produces the same observable effects as the action of one elementary charge crossing the membrane n times during the same period of time. They're practically indistinguishable, and we can express such actions mathematically using the equation. The action Hn equals n times the energy E0 over the time interval T0. N charges crossing the membrane once per lifetime is denoted as En times F0, and one elementary charge crossing the membrane in 1/nth of the time is denoted as E0 times Fn. Both expressions yields the same physical quantity. With all the base units defined, we can model the ion crossing through a specific channel using the complex function phi n, which is equal to e raised to the power of I2 pi times the frequency Fn times t. Here, e is the base unit of natural growth, I is the imaginary unit, and 2 pi is the radians of an unit circle. Fn represents the number of particles produced by an ion channel per unit of time. The function phi n models the evolution of different generations of particles originating from a common ancestor. The lineage information is encoded and translated by the ion channel that controls both the type of passing ions and the frequency of the actions. Phi n can also be expressed in terms of a particle's energy En and the unit action h0, where En times t divided by h0 is the total actions executed through a particular ion channel. Phi n, in this form, is known as the time-dependent wave function. Channels that operate at the same frequency n are represented by psi n, which is the product of the unit function phi n and the coefficient Cn. The modulus of Cn is the square root of the number of channels, and its phase angle indicates the relative execution frame of channels with frequency n. Ion crossings in a brain can be represented by a single function, psi, which is the sum of all possible psi n. If a frequency n doesn't exist, psi n is set to 0. The frequency can be 0. E raised to the power of 0 equals 1. So psi 0 is the same as the coefficient C0, representing the system's bias. The brain has hundreds of ion channels and pumps, each with unique frequencies and coefficients, represented by these rotating arrows. The function psi can be visualized by adding up all rotating arrows. The combined arrow produces intricate patterns. Each pattern corresponds to a distinct brain activity. The density pattern of ion crossings corresponds to patterns of electric current, membrane potential, of energy consumption, which can be observed and tested through experiments. We can compute the density of ion crossings by integrating the density function derived from psi over a time interval delta, where delta represents the temporal resolution of an observation. A typical observable behavior lasts much longer than individual ion crossings, which are denoted by delta as greater than the maximum value of tau n. There are many notations on this screen. If you feel a bit overwhelmed, you can pause the video, ponder for a moment, and make sure that you fully understand all of them. Let's take a look at the integral one more time, as there may be a potential issue to consider. The integral is supposed to compute the number of net ion crossings as a function of time. However, the result seems to suggest that nothing changes over time. The channel's type and quantity are determined by gene expression in our brain, which does not change as frequently as our thoughts. The size of the observation window is chosen by the observer, which has nothing to do with the behavior of the observed. Given a specific observation window, all three terms remain constant, implying that the number of net ion crossings must also be constant. If a brain's ion crossings never change, it would be a dead brain. So, what's wrong with our interpretation? When individuals gaze up at the sky, they usually see only the attention-grabbing stars and galaxies, ignoring the vast empty space between them. They are surprised to discover that the so-called empty space is brimming with energy. Likewise, when people scan a brain, they typically observe only action potentials and not the resting membrane potential, which encompasses a vast region of cell membrane. The resting membrane potential remains stable because there is a nearly perfect balance between two opposing actions in most regions. The observed fluctuations in activity are temporary and local imbalances within a dynamic system. Overall, the system remains in a state of equilibrium, with the number of net ion crossings being 0 for the majority of the time. Thus, what's expressed in the result is statistically accurate. A follow-up question would be, which term here is responsible for these local imbalances? The frequency n represents the type of ion channels, something genetically hard-coded in a species. In other words, n cannot change on the fly. The only variable that can change is the weight Wn, which represents the number of ion channels of different frequencies. It is unlikely that this change is brought about by gene expression, which is a slow and costly process. Therefore, the task must be performed by the pre-existing ion channels. To understand how these mindless particles empower us with unlimited imagination, we must be able to model how the system evolves not only over time but also in space. If you find the content in this channel is interesting, please click the like button below, subscribe, and share it with your friends. It will help to connect those who are also interested in the topic. Thank you very much for your help.